Hello and welcome back to our lesson on MTH. This week we are going to start lesson 2 as I said last week, and we are going to be more advanced in what we have been doing last week. We are going to see more definitions, more calculations and more forms. Okay, first of all, let me thank you guys for your participation in the group chat. People commented, we also saw a lot of questions that day. And people that asked the idea, they actually did well in helping to solve those questions. So I also implore us to perform more this week as we be considering the lecture. Thank you. Very quickly, let's move to today's tutorial. And the first thing we're going to be considering today is order and degree of differential equation. By the end of this class, we should be able to see how they classify differential equations into their order and their degree. But before we start that, let's take a look at some definitions so you're able to set some foundations for our class today. So we have definition A that says that the order of a differential equation is the order of the highest differential coefficient present in the equation. We are going to really need this later in the class. Just let's take a look at this very well. The definition says again that the order of a differential equation is the order of highest differential equation present in the equation. We are going to use some examples to illustrate this, but first let's talk about the B part of the definition. It said the degree of a differential equation is the degree of the highest differential coefficient which appears in the equation after moving a radical sign and fractions. I think it will be better for me to use examples to illustrate these examples. So examples, so we are going to talk about the first part. Now let's take a look at this equation very well. We have the y of d is equal to a cos x, and we're told is in first order and first degree. So now let's go back to our definition, which says the order of a differential equation is the order of highest differential equation present in the equation. We all know that this is the first order differential equation, which is only the y over dx. Here we are not talking about any d square y over dx square. It's only the y over dx, and which is the first order. And we consider that the highest power of the y over dx here is still 1. So here we now have first order and first degree. So let's take a look at the second example. We have the square y over dx square. When we look at this, we know that this is the second order because of what? We have the square here, right? That means after we have differentiated a particular equation 2 times, that's when we are going to have what? This thing. So we are in what? Second order. And the highest power of the y over dx here is still what? 1. Let me quickly illustrate that by bringing out the third example. Now here we have what? An equation in second order and second degree. We say that everything here is now raised to the power of what? 2. This is square. Everything is raised to the power of 2. That means the coefficient is in what? Is in power of 2, as you can see in what? Definition B. So we have the other in the second order, and the highest power to be what? 2. Let's look at that in equation 4. This is first order, but the power is what? Square, which means this equation is in first order and second degree. We should take a look at it very well. This is in first order first degree, second order first degree, second order second degree, and first order second degree. So as we look at that, we are going to be taking a look at some examples. But before we start, let's form a basis for what we are going to be discussing in our examples. Okay, we are going to be considering first order linear differential equations. This is going to be the basis of majorly what we are going to be covering in this part of the lesson. Okay, there are some things that you have to know that the solutions of differential equations involve integration. So most of the time it is not possible in consequence to formulate rules. As with differentiation, that we easily form rules and solve whatever we want to solve. So in this lesson we shall discuss the standard methods of solving differential equations of the following types. It's not actually a law that guides them. As we proceed through the class, we are going to be seeing some methods we are going to be applying in solving some equation. So the first one we are going to be taking a look at is methods of solving differential equations of the following types. So the first one we have is direct integration method. We have variable separable. We have homogeneous differential equation, linear differential equation, exact differential equation, non-homogeneous reducible to. This is the first one you'll be considering, which is variable separable. If a differential equation can be written in the form f of y dy equal to q of x dx, this is the law that guides the workings of this part. We say that variables are separable, y on the left hand side and x on the right hand side. So we can get the solution by interpreting both sides. We are going to be seeing the calculations for this in the following examples and how to apply this law. You should take note of this very well. It's going to be very handy in the following examples. This is the first example we are going to be considering, and we have the question: solve the equation x plus 1 divided over dx equal to x y squared plus 1. To solve this equation, we are going to refer back to the last slide, which says f of y dy must be equal to what? Q of x dx. So our major aim is to bring all y's and dy to one half of the equation, and all x dx to the other half of the equation. So we are going to do this first by bringing the x to the right hand side. If you cross multiply, we have the x to this side and y will still stay in this side. We have x plus 1 dy equal to x y squared plus 1 dx. Now as you can see, we are not reached the place. We still have x and dy on this side, and we have y and dx on this side, and our major aim is to bring all x and dx to this side and all y and dy to the other parts. Now we are going to separate the variables in the equation by dividing through by x plus 1. So dividing through this equation through by x plus 1, we get this dy equal to what? X y squared plus 1 dx all over x plus 1. So we still need to multiply by 1 over y squared plus 1. You can actually try to solve it out in any way you wish to solve it. We multiply through by 1 over y squared plus 1. So now we have 1 over y squared plus 1 dy on one part, and 1 minus 1 over x plus 1 on the other part. Here we consider that we have y and the function of dy. We have x and function of dx. So the next thing is to integrate this equation. Now you have to pay attention and be very familiar with this. In most of our questions, we are going to be integrating when we reach this point. After we have already gotten our x and the function of dx on one side, y and the function of dy on the other side, the next thing for us to do is to integrate both sides. Now if we integrate this side, it might be a little too tricky because we have to refer back to trigonometry ratio, and this is the simple I have bring out here. Integrating this, we have the answer to be tan inverse of y. You can actually check through the solution here. Now if you integrate 1x, we get x, and if you integrate 1 over 1 x plus y 1, we get ln 1 plus s, and c is the constant of our integration. So let me quickly bring out the answer by shifting tan inverse to the right hand side. We now have y equal to tan x minus ln 1 plus x plus c, which is the constant of integration. Now that's it for our first example. We are going to be following the same pattern in all the other examples. Moving quickly to the second example, we have the question: solve the equation 1 plus x y dx plus 1 into brackets 1 minus y x dy equal to 0, and we all know that this one can actually be omitted here. Let me just clean it. Now still following the same sequence, separating the variables in the equation. So we have y minus 1 over y dy equal to x plus 1 over x dx. So I arrived this through the process I did in the last example. We bring all our dx to one side and all y's to the other side. Now the next for us to do is to integrate both sides of the equation. Now if you are integrating this, it might look a little bit tricky, but I bring out the solution here. So if you are integrating this, you can actually apply this method, y over y minus 1 over y dy equal to 1 over x plus. You should check through this. You should check through this. The solutions is there. Then we are going to get our final answer, which is this, and this will be the answer to the example generally. This is the third example. The question says solve the equation dy over dx equal to e to the power of x plus sine x. Now there's one thing we are going to notice here. This is actually another form of the question. Here there's no any function of, there's no any y variable. All we have is x here. So I quickly put a note that if one variable is absent, the equation is going to be integrated directly. So there's no need to put the y over dx in one side, put y in one side, put x in one side. So we bring x to the other side. Since there's no y, there's no further calculation, we bring x to the x to the right hand side, and we have dy equals to ex sine x dx. As you know, the next thing to do is to integrate both sides. So if you integrate dy and integrate this equation, integrating dy, we are going to get what? Y. And if we integrate this, we are going to get what? Ex minus cos x plus c. If we integrate e to the power of x, we get what? E to the power of x minus. And if we integrate sine of x, we get what? Minus cos x plus c. You can see this one is quite simple. That's going to be the solution to this example. Straight to example 4. We have the equation, we have the sample. Solve the equation dy over dx equals 10x squared, and this is very similar to the one we did last example. That's example 4. Example 3. Here there's no any variable y. We have to bring x to the right hand side and integrate directly. So bringing x to the right hand side, we have dy equal to what? 10x raised to the power 4 dx. So we integrate both sides. If we integrate the y, we are going to get y, and if we integrate this, we get this. So after integrating the y, we get y, and after integrating this, we get what? 2x raised to the power 5 plus c. It's going to be what? This is going to be what? 10 x raised to the power of 5, everything all over 5. So 5 will go here and 5 will go here, making this place to become 2. And we're going to get 2 x raised to the power of 5, as you can see. Example 5 is the opposite of what we have seen in example 3 and example 4. We saw in example 3 and 4 that we only have the function of x with no function of y, but here we have the function of y and no function of x, no variable x in this equation. Now, as we used to do in example 3 and example 4, we bring the x to the right hand side and we integrate directly. But if we choose to bring the x to the right hand side, we are going to have the function of y and the x, which is not what we are supposed to get. So what we have used to do here is to flip the equation, changing the y over dx equal to what? Dx over dy, and then we have to flip what the coefficient is equal to, which is what? 1 over tan y. Now is to integrate both sides. We integrate dx after we have already bring the y to the right hand side, and we integrate 1 over tan y. Now integrating x, we have what? Dx, we have x, and integrating 1 over tan y, we have ln of sin y. This is a conversion. It has the way it's been proved. We won't cover that in this lesson. So integrating 1 over tan y, we have ln of sin y and plus c, which is the constant of integration. Now if we choose to make y the surrogate formula, which is what the aim of the example is, to make y the surrogate formula and derive the normal equation. So ln of sin y equal to x minus c, and here we have sin y equal to exponential x minus c. Now the way we got the exponential is to divide through by x ln, which will then give us what? Exponential of e minus c. You can write this thing in indices form to get it is e exponential x and exponential minus c. Now the answer is now y equal to sine inverse of a exponential x. A is being drawn from changing everything here into a. So exponential minus is being changed to a. Just to simplify our equation, we have y equal to sine inverse of a exponential x. This is our last example, which is example 6, and the question goes like this: solve the equation 1 minus x divided over dx plus 1 minus y equals 0. And this is like another method, different entirely from the first one, the second one, the third one, the fourth one, and the fifth one, and is very similar to what we did in example 1 and example 2. So first thing we are going to do is to separate the variables, and we have 1 over 1 minus y dy equal to 1 over 1 minus x. Getting this is what I did in example 1 on how to separate equations, make all dx to be on one side, all x and y to be on one side, and all y and dy's to be on the other side. Next thing now is to integrate both sides. We integrate 1 over y minus 1 and 1 over 1 minus x. We are going to arrive this integrating 1 over 1 minus y, we have what, as we all know, ln y minus 1, and integrating 1 over 1 minus x, we have minus ln 1 minus x plus the constant of integration. Now there's a way we can still extend this further, so I make out a little sketch here. If we go through this, I extended this further, I simplify it further, and I derive it y equal to 1 plus exponential c all over 1 minus x. Now as we did in example 5, if we make a to be equal to exponential c, we are going to get our y to be equal to 1 plus a all over 1 minus x, which is actually what we get here. Y equal to 1 plus a bracket 1 minus x, everything is power of minus 1. So this is our last example. I hope you understand. If there's any question or anything you want to add, we will meet at the forums and the groups. We are going to be giving out the exercise. Please endeavor to study them, prepare to answer people's questions when we meet for the evaluation of the class. Thank you very much. You have come to the end of the class, and this is going to be our exercise, our assignment. So let's go through everything. If there's anyone giving any problem, we should bring it during the group chat. We look at it together, and we're going to solve it together. Thank you very much. See you in the next tutorial, the next class, which is going to be next week. Thank you.